All right, in section 7.3, we're starting to learn about vectors. And in this section, I'd really like to encourage you, if possible, to use graph paper because the accuracy of the length of each line and direction becomes really important. Because well, I'll tell you why. Because vectors are, vectors have magnitude, which describes a size, and it has direction. So, for example, what we've seen so far is scalars, which is like the size of a magnitude. So that's size only, but now we're going to add some direction. So, for example, the number 5 is a scalar. It doesn't have any other information on about it. I could even say 5 feet, and there's their distance. It's still just a scalar. But if I say 5 feet at 30 degrees, then it looks more like, 30 degrees here, and this length is 5 feet. So that is a vector. It's got direction, and it's also got size or magnitude. So, for example, if we open up our textbook for our classwork, let's see. Let's look at number 8, for example. Then we're told that as part of a family reunion activities, the Williams clan, you know what, I'll just go ahead and get the picture for you. Okay, so I got the problem here where we got our family bowling alley activity, and we have Granddad in line 1 who rolls a ball at 50 feet per second. So that's strength. So magnitude can be size. It can be a number of feet, but it can also be like a number of pounds. The weight or the strength or the distance. It can be a lot of different ways to measure size. So in this case, we're measuring that size of how many feet per second he got. So let's say one little tick mark here is 10 feet per second. So let's do 5. So it makes a little longer line. So that means Granddad got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So there's Granddad's vector. He bowls in a straight line to the pin and at a distance, or I should say magnitude, of 50 feet per second. That's Granddad. So I'll just call that guy GD. And Papa, let's see, Papa's in lane 2 and gets 60 feet per second. But it's in the same direction because they're going parallel to each other. So Papa would be over here. Doesn't matter about the location, actually. What matters is the direction. And he gets 60 feet. So he's got his 50 plus another 10 feet, which makes his vector look like this. Here's Papa at 60 feet per second. So it's a little bit longer. He's got a little more force. So the vector's length represents that force. The ball didn't travel further. So to represent these lines as like the path of the ball would be incorrect because the ball's traveling the same distance, but it's got more force. And that's what the length of the line is representing. And then we have our last little guy here, Junior, who gets 30 feet. And that's going to be half of the 60. So the graph paper is important because you're, let's see, 1, 5, 10, one more than that. So that says Junior. He's got 30 feet per second. So the graph lets me be accurate about the length of each line in relation to the other lines. So notice that green line is exactly half of the purple line because the force of Junior's ball is exactly half of the force of Papa's ball. Now again, their balls travel the same distance, but this vector is not measuring the number of feet that were traveled, it's feet per second. So it's the amount of force that they're putting on that ball. All right, so that is an example of representing those 3 different vectors. They're all going in the same direction. So each of those 3 lines represents direction and magnitude. We see another example of how to show a vector in number 12, where we have Two brothers pulling on a mule's harness. So let's kind of draw the harness. Poor little mule here being drawn by me. Yeah, it's a cute little mule. Mule. Here's his harness. And let's see, we got Jackson and Rupert are pulling at it. So Jackson's pulling at a force of 200 pounds. While Rupert, a little more upset, is pulling at 220. So his line's going to be a little bit longer. And we see the angle between these is 16 degrees. So again, we have direction in relation to each other. So even if it's like this or like this, as long as that's 16 degrees, the relationship I have for direction is the relationship between those two vectors. So there's another way to represent those vectors: direction and magnitude. And then we see another example with number 13 and 14. So this one's kind of a more graphical example here where they give you the ordered pair of the initial point and the terminal point. So if I have a axis here, let's see, so my initial point's at -3, 2, so right here. And my terminal point is at 4, 5, so that's 1, 2, 3, 4, 1, 2, 3, 4, 5. There's my terminal point. Then I can draw a line between those two. And the terminal point shows the direction. So that's, let's see here. Starts at the initial point. So there's a point there, and the arrow at the terminal point to show the direction. So it's kind of like a ray. And this graph says this. Oh, actually I did number 13, didn't I? Okay, so there's 13. There's my initial point at -3, 2. My final point at 4, 5. I'm going to duplicate this so I can show you what the position point looks like. Whoops. So, and then to find the position vector takes this same line and it just looks at the change, the vertical change and the horizontal change. Ugh, I'm having a hard time getting just this line, not the two. Oh well. And it lands there, sort of. So this is a position vector now. This is the position vector that corresponds with the vector for number 13. This is the position vector. And the position vector, I'll express these with these little brackets that show me that it's measuring these in components. So the horizontal component is 1, 2, 3, 4, 5, 6, 7. That's the -3 and the 4. And the horizontal component is 1, 2, 3, the distance between 2 and 5. So that these little brackets here show me that that is not an ordered pair, but it's a vector in component form. Where, let's see, this here is the horizontal component, 7, and this is the vertical component. So here's a snip from your book kind of summarizing that. So for given those, our vector is described with a initial point and our terminal point. Then we find the position vector by finding that horizontal distance for the horizontal component and the vertical distance for the vertical component. And we start and we just kind of move it over so the initial point is at 0, 0, and its terminal point shows those components. So once I have a vector in that position component form, I can find its magnitude. So let's take this one for an example. So if I have a vector, let's call it V. What was it again? 7, 3. So its horizontal component is 7, vertical component is 3. Then I can find that magnitude of that line. I'm going to make this a little smaller so I can look at the vector at the same time. Actually, you know what? I'll just move book right here. So that magnitude of this vector here, would just be that line. So you can kind of draw that imaginary triangle here to see and use a Pythagorean theorem to find that magnitude of the vector, which is written like this. So it's absolute value bars to show the size of the square root of the horizontal component plus the vertical component. So that's 49 plus 9, so square root of 58, whatever that is. And then the direction of this, we can use trigonometry to describe this direction. So we have, if we call that theta, then that theta, using that imaginary triangle, would be, let's see, tan inverse of the, let's see, tan is SOHCAHTOA, opposite over adjacent. So it would be the horizontal component over the vertical component, which works good for this one. Even if it was an obtuse angle, we could use this as our reference angle. So I'm going to get that from your book, and then we'll try some new problems in a next recording. So there's a summary on page 346 where I got this that demonstrates, kind of summarizes all that information, which will apply to some problems in the next recording.